Hello everyone, this is Kanjula Ramakoti Reddy speaking from IIT Roorkee DSCI second year. I am going to present you the topics eigenvalues, eigenvectors and diagonalization. So now let's begin with eigenvalues and eigenvectors. So firstly, what are eigenvalues and eigenvectors? So let's say these are some special numbers and special vectors. So why we need to calculate this we're gonna see later. And now let's begin with eigenvalues and eigenvectors. So let V be a vector space over field F and T be a linear operator on V. What is T? T is a linear operator on V. T is a matrix which may change or may not change the direction of some vectors in the vector space. Any non-zero vector V from vector space is called an eigenvector of T matrix, which is linear operator, if some scalar lambda such that T into V equal to lambda V. When we When we give any input vector v to linear operator t, the output should be in the direction of the input vector or opposite to the input vector. So such vectors are called eigenvectors, and this scalar lambda is called eigenvalue corresponding to the eigenvector v. A square matrix A may be viewed as linear operator t. Define t of x equal to ax, where x belongs to vector space v. So now let's see the definition of eigenvectors and eigenvalues. Let A be a square matrix of order n. Then consider the homogeneous system of equations shown below. Ax equal to lambda x. The values of lambda for which system of linear equations has non-trivial solutions. The values of lambda for which the system of linear equations has non-trivial solutions. What is non-trivial solutions? We will see in the next slide. Are called eigenvalues, and the corresponding non-zero vectors x are called eigenvectors of A. If the homogeneous system A minus lambda I into x equal to 0 has a non-trivial solution, then rank of the coefficient matrix is less than n. The coefficient matrix A minus lambda I is singular. How we gonna see now? So let A be a square matrix of order n and the homogeneous system of equations Ax equal to lambda x, where x not equal to 0. Here lambda is called eigenvalue of A and x is called the corresponding eigenvector of A, for which its eigenvalue is lambda. Ax equal to lambda x. When we bring this lambda x this side, Ax minus lambda x equal to 0. This lambda x can also be written as lambda ix, where lambda i's dimension is n and a's dimension is also n. So we can take a minus lambda I into x as common, which is equal to 0, and x as not equal to 0, where a minus lambda I into x equal to 0 and x not equal to 0. So there exists at least one x where a minus lambda I into x equal to 0. So nullity of a minus lambda I matrix is greater than or equal to 1, and dimension of A minus lambda I matrix is equal to n. From the rank nullity theorem, rank of A minus lambda I plus nullity of A minus lambda I should be equal to the dimension of A minus lambda I. So rank of A minus lambda I is equal to dimension of A minus lambda I minus nullity of A minus lambda I. As nullity is greater than or equal to 1, the rank of the matrix A minus lambda I should be less than or equal to n minus 1. So what does that mean? What does the rank of A minus lambda I is less than or equal to n minus 1 mean? The dimension of A minus lambda I matrix is n and the rank is less than the dimension. So when you write the row echelon form of the matrix, there exists at least one row where it is completely zeros. So when there exists one row, it's completely zeros and its determinant value is 0. So we can write det of A minus lambda I equal to 0, which is characteristic polynomial of lambda. As seen in the previous slide, det of A minus lambda I is equal to 0. Det of A minus lambda I is shown here in the figure. And here Pn of lambda is det of A minus lambda I, which is equal to minus 1 whole to the power of n into lambda power n minus c1 into lambda power n minus 1, and so on. This is a general characteristic polynomial shown here. So this equation is called characteristic equation of matrix A, and the roots lambda 1, lambda 2 and so on lambda n of the characteristic equation are called eigenvalues. So now let's see an example. Let A equals to this 1 minus 1 1 1. Find the eigenvalues and the corresponding eigenvectors of A. So now let's answer this question. A equals to 1 minus 1 1 1. So first we have to find the eigenvalues of the matrix A and then the corresponding eigenvectors of A. So to find the eigenvalues of the matrix A, we can find the determinant of A minus lambda I equal to 0. So the determinant of A minus lambda I, which subtracts the value lambda from the diagonal elements, which is shown here. And after solving this equation, we will get the values of eigenvalues as 1 plus I and 1 minus iota. And now let's find the eigenvectors corresponding to the 1 plus I and 1 minus I. So eigenvector corresponding to 1 minus iota, which is A minus lambda I into x equal to 0. A minus lambda, we will substitute the value 1 minus I in place of lambda. A minus 1 minus I into I identity matrix into x equal to 0, which gives I minus 1 1 I into x1 x2 equal to 0. After solving this, we will get x1 plus ix2 equal to 0, as the eigenvector is x1 comma x2. So we will substitute the value of x1 as minus x2, and then we will take the value of x2 common. So minus I comma 1 are left. As we have seen in the previous slide, the eigenvector we got is x2 into minus I comma 1, which is not a single eigenvector. We can get different eigenvectors by taking different values of x2. So many times after getting eigenvalues and then solving for the eigenvectors, we don't get a single eigenvector, we get a series of eigenvectors generally. In such cases, we can choose one of the possible eigenvectors as eigenvector. Generally, we consider special solution by taking the values of free variables to be 0 or 1 and then get the values of other variables. In the above question, x2 is free variable, so we can take the value of x2 to be 1 and then we can say all the multiples of that vector minus I comma 1 are eigenvectors. So as said in the beginning, eigenvalues and eigenvectors. Why are we calculating this actually? What does they actually mean? What does they mean in the physical sense? For example, you can take a matrix 3 0 1 2, which we can also call a linear transform operator, where 3 comma 0 is in this direction and 1 comma 2 is in this direction. So these are the two basis vectors I choose and for the linear transformation operation. So consider the following linear operation matrix 3 0 1 2 as shown in the above figure. Let's say the matrix as A and any vector x acted upon A gives the vector Ax as output, which may or may not lie in the vector x, span of vector x. So span of vector x means the line passing through origin and the vector. In most of the cases, it won't lie in the span of vector x after the linear transformation, but some special vectors lie on the span of vector x. So these special vectors will just get stretched or compressed in the direction of span of vector x. So all such special vectors are called eigenvectors, and the factor by which it's getting stretched or compressed is called its corresponding eigenvalue. So this is my linear transformation matrix 3 0 1 2, where my bases are 3 0 and 1 2. So now let's consider some random vector for linear transformation. So this is the some vector and this is the span of vector which its direction is not changing along this span. So what is given here? Most vectors get knocked off their span after the linear transformation. Let's consider some vectors and apply linear transformation. So this is the graph before linear transformation. So this is the graph after it is applied through linear transformation. After linear transformation, we can see the vector got knocked off their span. So what is span? This pink color line shows the span of the previous vector, and after applying this linear transformation, this is 1 comma 2 and 3 comma 0. After applying this linear transformation, it gets knocked off that span. It gets rotated from its original position, so its direction got changed. So in the previous slide, we considered a different vector and its direction got knocked off their span, but there may be some condition such that the direction may not be changed. So what is it? But as we discussed it before, some special vectors even after linear transformation lies on the span. So there may be some special vectors which may does not change its direction even after applying the linear transformation. So this is the linear transformation, and this is the vector we are considering now. So this is the graph before linear transformation, and now let's see the graph after linear transformation. It will change its direction or not. So this is the graph after the linear transformation by applying 3012. So this is the span we have chosen in the previous slide, and the vector remains on its own span. It doesn't change its direction. It just got stretched by 2 times. So this is some kind of special vector we are thinking of. And you can see some another vector which lies on its own span. So this is the graph after applying the linear transformation. So we have chosen 1 comma minus 1 comma 1, and after linear transformation its direction remains in its own span, and it's just got stretched by 2 times. So from the previous observations we can say that if you choose any vector in this direction and we apply the linear transformation, it will get stretched by 2, and if we choose any vector in this direction, in the x-axis direction, it will get stretched by 3. We can see that some special vectors getting stretched or compressed by but lying on their own span, and some vectors getting knocked off their span. As we can see, vectors in this direction got stretched by 2, and vectors in x direction got stretched by 3, and all the other vectors got rotated from their direction and got knocked off their span. They doesn't lie in their own direction. So such special vectors are called eigenvectors, and factor by which they are getting stretched or compressed is called eigenvalue of the corresponding eigenvector. The vectors which don't change direction by applying the linear transformation are called eigenvectors, and the value by which they are getting stretched or compressed. Here the eigenvectors with eigenvalue 2, which means when you apply linear transformation by taking any vector in this direction, they will get stretched by 2 times. And here it shows the eigenvectors with eigenvalue 3. If we choose any vector in this direction and apply linear transformation, it will get stretched by 3 times. So these are eigenvectors with eigenvalue 2, and these are eigenvectors with eigenvalue 3. So these special vectors and special values are called eigenvectors and eigenvalues. So I guess you have understood the physical significance of eigenvectors and eigenvalues. So the question is, can eigenvalues be negative? Yes, of course, eigenvalues can be negative, which means after the linear transformation, the vector gets flipped. So if the vector is facing towards the positive direction, it will face towards the negative direction after the linear transformation, and it may get stretched or compressed by the factor of its eigenvalue. There can be no real eigenvalues, there can be single eigenvalue, there can be two eigenvalues, and so on. There can be many cases following to the vector and the matrix A. Sometimes there can be no real eigenvalues, which means every vector rotates by its transformation. For example, you can take 90-degree rotation matrix as shown in figure. The matrix is 0, minus 1, 1, 0. This is 90-degree rotation matrix which rotates every vector by 90 degrees. For example, we are considering this is this vector and this is its span. So we will see what happens after linear transformation. So you can see the graph after rotation. So this is the span which is shown in previous figure, and it rotated by 90 degrees. You can see 90 degrees here. This is 90 degrees. The above matrix doesn't have real eigenvectors as it rotates every vector. So when you try to find eigenvalues, you will find the eigenvalues to be complex values. So we can say there are no real eigenvectors as it rotates every vector. There is even a possibility that all the eigenvalues are same, which makes there is only one linearly independent eigenvalue, and a single eigenvalue can have more than a line full of eigenvectors. For example, you can take scaling matrix. This is scaling matrix which is 2i, 2 0 2 2, scales everything by 2. For example, you can take this vector, this vector, and this vector. This is before scaling, and after scaling it becomes 2 times. Every vector becomes 2 times. So this is the graph after applying the linear transformation. you can see the vector lies in its own direction and it becomes 2 times. So every vector in this plane becomes 2 times after applying this transformation. So the eigenvalue is 2 and the eigenvectors are all the vectors which lies in this plane. So we can say that if the eigenvalue can have more than a line full of eigenvectors, there can be different lines of eigenvectors. So now let's talk about the application of eigenvalues and eigenvectors, which is diagonalization. So before diagonalization, we will talk about a similar topic to diagonalization, which is similar matrices. Similar matrices. What are similar matrices mean? So let's say A and B are two square matrices of order n over the field F. If we will say A is similar to B, so there must be existing a matrix P, which B equal to P inverse AP, where P is an invertible matrix. Then we can write symbolically A is similar to B. If we are saying A is similar to B, which means that B equals to P inverse AP, where P is an invertible matrix. So when we are saying A is similar to B, which means that B equals to P inverse AP and there exists some P which is invertible. And when we say A is similar to B, it is obvious that B is similar to A. How? It is given down. It can be proved by taking P inverse equal to K. If you are taking P inverse equal to K and then A becomes A equals to K inverse BK. So we can say B is similar to A and A is similar to B. Both are obvious. Similar matrices have same eigenvalues, though eigenvectors are different. So let's say A is similar to B. What does that mean? What does A is similar to B mean? There exists some P such that AP equals to PB or A equals to PB P inverse. If Ax equal to lambda x is the eigenvector of A and lambda is the corresponding eigenvalue and x is not equal to 0, which is necessary condition to be an eigenvector. So by substituting A equals to PB P inverse in the Ax equal to lambda x, which gives PB P inverse into x equals to lambda x. So by multiplying with P inverse on both sides, which cancels P here, by multiplying with P inverse cancels P here and multiplies with P inverse here. After multiplying with P inverse, we can see B into P inverse x equals to P inverse into lambda x. After rearranging the terms, B into P inverse x equals to lambda into P inverse x. So by taking P inverse x equal to y, By equals to lambda y, where x is the eigenvector of A and lambda is the eigenvalue of A, and the same eigenvalue comes for B. This is only true if y is not equal to 0. Let's prove this by contradiction. Suppose if y equals to 0, y is P inverse x. So P inverse x has to be 0. As P is invertible matrix, we will multiply both sides by P. So x has to be 0, which contradicts that x is not equal to 0. Hence y is not equal to 0. As y is not equal to 0, it is eigenvector of B and lambda is eigenvalue of A. So A and B are similar matrices which have same eigenvalues. So which means that similar matrices will have same eigenvalues. This is important property we will use in further slides. So to diagonalize a square matrix of order n cross n to D, which is diagonal matrix D1, D2 and so on Dn. So AP equals to PD. So there exists some P which satisfies this condition. So we can say A equals to PD P inverse, where D is a diagonal matrix. From here we can say A is similar to D, which means A and D are similar matrices, which also mean that A and D are going to have same eigenvalues. When A and D are going to have same eigenvalues, let eigenvalues of A are lambda 1, lambda 2 and so on lambda n. So eigenvalues of diagonal matrix are same as the elements of the diagonal matrix in the diagonal. So they both are going to have the same eigenvalues and the eigenvalue should be present in the diagonal as shown here. D equals to lambda 1, lambda 2 and so on lambda n. A and D are having same eigenvalues. Since the diagonal matrix is made of eigenvalues of A, the matrix P should be made of eigenvectors. The diagonalization of A is possible if A has unique eigenvalues, or it has two or three or more than two or three similar same eigenvalues, and if they have different linearly independent eigenvectors, then also diagonalization is also possible. The matrix P should be made in the same order in which the matrix D is made. For as shown in the previous slide, the matrix D is made lambda 1, lambda 2, and so on. In the same order, the matrix P also should be made. In the first column, the eigenvector of eigenvalue lambda should be kept, and then the eigenvector corresponding to the eigenvalue lambda 2 should be kept, and so on. The matrix P should also be made in the same order in which the diagonal matrix D is made. So now let's solve some problems related to diagonalization. Let A equals to this given matrix. The eigenvalues of given matrix A are 2, minus 4 and x. So first we have to find x, and also we have to verify that whether A is diagonalizable or not. So A is the given matrix here, and the given eigenvalues are 2, minus 4 and x. So we know the property that sum of eigenvalues 2, minus 4 and x should be the sum of the elements in the diagonal, which is trace of A. So x is found out to be 2, and the eigenvalues are 2, 2 and minus 4. Here 2 is occurring 2 times. So now we have to check that the eigenvalue 2 has two linearly independent eigenvectors or not. If there are two linearly independent eigenvectors, then A is diagonalizable. If there are only one linearly independent eigenvector, then A is not diagonalizable. So now let's check for the eigenvalue 2. A minus lambda I into x equal to 0. For lambda equals to 2, a minus 2i into x equal to 0. After substituting a minus 2i here, 1 minus 1 1, 7 minus 7 1, and 6 minus 6 0 into x1 x2 x3 equal to 0. After performing certain operations, we can see that there is only one linearly independent eigenvector exists for lambda equals to 2. Hence, A is not diagonalizable as there are no two linearly independent eigenvectors. So now let's discuss the most important application of diagonalization. So let's consider some matrix B which is diagonalizable. Let the eigenvalues of A are 3, 3, lambda. So now first we have to find the lambda, and then we have to see it is diagonalizable or not by checking there are linearly independent eigenvectors existing to 3 or not, and then we have to check the diagonalizability. So after checking the diagonalizability, we have to find the value of a power 10 and e power a. So this is the given matrix, and then eigenvalues are 3, 3, lambda. By using the property sum of eigenvalues is equal to the trace of a, you can find the value of lambda. You can find the lambda is 5. So the eigenvalues are 3, 3 and 5. For lambda equals to 3, now let's find the eigenvectors and check whether there exist two linearly independent eigenvectors or not. So a minus 3i into x equal to 0. 1 comma 1 comma minus 1, 2, 2 minus 2, and 1 comma 1 comma minus 1 into x equal to 0. Here we can find x1 plus x2 minus x3 equal to 0 is the only equation, and we can find two linearly independent eigenvectors. For lambda equals to 5, we have to find the eigenvector a minus 5i into x equal to 0. We can find the eigenvector to be 1 comma 2 comma 1. As we have discussed earlier, the diagonal matrix is made of eigenvalues. The diagonal matrix is equals to 3, 3, 5, where 3, 3, 5 are eigenvalues. And the corresponding vector P is made of eigenvectors, which is in the same order. Which means in the vector P, in the matrix P, we have to place the eigenvectors in the similar manner. We have to place the eigenvalues of 3 in the first two rows, first two columns, and then the eigenvector of 5 in the last column, in which way we are placed. So AP equals to PD, which means A equals to PD P inverse. So when we try to find the value of A square, A into A, it found to be P D square P inverse. In the similar manner, if we continue, a power k equals to p into d power k into p inverse, where a power 10 equals to p into d power 10 into d inverse, where a power 50 equals to p into d power 50 into d inverse. where P inverse can be found by getting inverse of P, and we can find the powers of diagonal matrix very easily. For example, if we have to find d power 10, we can directly give the power to the diagonal elements. We get d power 10 equals to 3 power 10, 3 power 10, 5 power 10. So it is easy to find the power of diagonal matrix compared to the original matrix. So we can find the higher powers of any matrix by diagonalization in a very easy manner. As we have found a to the power of 50 in the previous slide, let's find e to the power of matrix. It is possible to find e to the power of matrix by using diagonalization. Let's see how. So by using the expansion e to the power of x, e to the power of x equal to 1 plus x by 1 factorial plus x square by 2 factorial and so on. By applying same expansion to the matrices, e to the power of a equals to I plus a by 1 factorial plus a square by 2 factorial plus and so on, where a equals to p d p inverse and d is the diagonal matrix made of eigenvalues and p is the matrix made of eigenvectors. So by multiplying P inverse on the left and P on the right, which gives P inverse P plus P inverse AP by 1 factorial plus P inverse A square P by 2 factorial plus and so on, which is equals to I plus P inverse AP, which is diagonal matrix D, P inverse A square P, which is diagonal matrix D square, is equals to I plus D by 1 factorial plus D square by 2 factorial, which is equals to e to the power of D, where e to the power of d equals to I plus d by 1 factorial plus d square by 2 factorial plus and so on, which is equals to I plus, where diagonal matrix is lambda 1 lambda 2 lambda 3 by 1 factorial plus lambda 1 square lambda 2 square lambda 3 square by 2 factorial plus and so on, which results in adding of first elements together, which is 1 plus lambda 1 by 1 factorial plus lambda 1 square by 2 factorial plus and so on, which is e to the power of lambda 1. And similarly we will get e to the power of lambda 2 and e to the power of lambda 3. E to the power of diagonal matrix is e to the power of its elements. So P inverse e to the power of a, P equals to e to the power of d, which means e to the power of a equals to P e to the power d and P inverse, where d is e cube and e to the power of 5, where d is 335 as shown in the previous slide. So by using diagonalization, we can find e to the power of a and 2 to the power of a and 3 to the power of a and many other exponential matrices also. It is very easy to find by diagonalization. And thank you very much for listening.